Okay, so I'll have 3 consecutive talks. I'll discuss some H-principle type results in symplectic and contact geometry. But most of the results were proved around 70s, very early 70s, and I'll also mention about some recent developments if we have some time. So what is H-principle? I'll first describe what is H-principle. It is a theory about partial differential equations or more general relations which can be inequalities or some other things. And it was often observed that if we consider partial differential relations in problems related to topology and geometry, the solution space is generally quite large, means there are a lot of solutions. So one can talk about the solution space. Informally what H-principle means is that so it's as it says, it's a principle. It means that whenever a differential topological problem or a differential relation has a formal solution, it has a genuine solution. So this is what the principle says. So how it is related to contact and symplectic, because as you have seen in Dhiraj's lecture, that contact forms and symplectic forms, they are defined by equations like this. And so this D that is appears is related to the differential. So they are solutions to certain differential equations or inequalities here. Okay. So I will first describe what is H-principle and its language. So let us start with first let us recall what we mean by a partial differential equation of order R. So this is a relation among its partial derivatives and then so something like this. This is a partial differential equation for functions, real valued functions defined on Rn and having Rth order differentiability. So let us denote it by 1. Now suppose we replace in this equation the partial derivatives by ordinary functions. That means we have, suppose I replace del f del xi, so these functions are coming from some other function. So these are partial derivatives. Instead, I will simply write aix. So these are, so del f del xi's, what happens to this? These are again functions from Rn to R. Here these ai's will therefore be some function from Rn to R. Okay. So I'll replace all these things minus. So this is what I mean by a formal equation. So I have a differential equation, I am replacing the partial derivatives by some ordinary functions, I get another equation. Similarly, ai's are also some functions from Rn to R, etc. So this will be called a formal equation associated with our equation 1. So as one can see that if your original problem has a solution, naturally this has a solution because you just plug in del f del xi for ai's, del 2f del xi del xj for aij's, so it will have a solution. That is immediate. So 1 implies 2. So there is nothing about it. Now what H principle asks is under what condition we can say that suppose you have a solution to this problem, then that would imply that your original problem has a solution. Now look at this equation. This is just an algebraic equation. There is nothing. It's just a topological. I just demand continuity of these functions. On the other hand, this demands, first of all, there is just one variable, and this demands that rth order differentiability of such functions. So H principle basically studies certain conditions on the equations. I'll explain those things, under which if we can show that the problem has a formal solution, then it will have a genuine solution. Okay. So 2 in H principle, it means 2 implies 1. So this is for functions which are defined on Rn to R. So this can be translated into functions between manifolds. So from now onwards, I will consider functions from M to N, and what kind of differential equation or inequalities that we consider. For example, let us look at this thing that I consider dfx is of maximum rank. So if your dimension n is strictly less than dimension n, then I can precisely write it down in terms of certain minors. So if you consider all k by k minors, for example, and look at that string of minors, this has to be a non-zero thing that expresses this condition as a differential inequality. On the other hand, suppose you start with, you have 2 Riemannian manifolds. Suppose they are Riemannian, G and H are Riemannian matrix. Then functions which are isometric, so it pulls back the metric H into G. If you expand this, this would mean like this. So in this situation, this is an inequality, whereas in this situation, this is a system of equations. So we consider such kind of partial differential relations. So instead of saying that it's an equation or inequality, we simply say this is a partial differential relations. So these kind of problems interest us. These are preserving certain structures. This is a functions of maximum rank and so on. So in the presence of any differential structure, you can talk about functions which preserve the structures. For example, if you have a symplectic form here, you have a symplectic form here, you can talk about functions which pulls back this symplectic form onto this symplectic forms. So you want to know when such problems has a solution. Also in the case of contact, suppose you have a contact structure xi and here you have another contact structure eta, you can ask for the existence of functions where dfx will map xi into eta, and this is conformal symplectic. Because just you notice that if xi is defined by some alpha and here say eta is defined by some beta, then d alpha when restricted to xi, that defines a non-degenerate form, And similarly, d beta when restricted to eta, that also defines a non-degenerate form. So the functions which preserve these bundles, that means take xi into eta, also a monomorphism, and pulls back this conformal symplectic structure onto the conformal symplectic structure here. So those kinds of maps are called isocontact maps. So these are certain examples of differential equations that will come in this discussion. Okay? We'll not discuss this one. So what is a partial differential equation in this context when you have a function f from m to n? So a differential equation, I will explain it in this language, right? Maybe 0 or maybe not equal to 0, whatever. Some relation between its derivatives. First derivative, second derivatives up to rth order derivatives. So that is a differential relation. Again, what is a formal solution? Formal solution would be, I'll be replacing these things by certain functions. So let us call this so this is another equation. So what are the values? This takes values in the certain bundles which are symmetric bundles, right? Because this is a second derivative of the function. So these are sections of certain bundles. So again the same question, if you have a solution to this, then you have a solution to that, and if you have a solution to that, under what condition you have a solution to this? This is the question. Okay, so let's first define something, notion called RZ. So you are suppose given a function from m to n, it may be just a local function defined on some open set. And suppose this is a point x in M, and we denote by this the infinitesimal information of the function f at x. So basically if you look at in the Rm to R level, then this is the coefficients of the Taylor's polynomial. You can think of this as the coefficients of the Taylor's polynomial. So this will be called the RZ. Look at this. This is a value taken in R. dfx is sections of certain bundle but just defined at one point. So this is something bilinear map. This is a R multilinear symmetric maps and so on. So this will be called RZ of f at x. Now let us look at what is R is equal to 1, because in most cases we will only consider the R is equal to 1 case. So J1 fx is simply means x fx and dfx. So what are the information? There are just 3 quantities related to J1 fx. This is a point in M, this is a point in N, and this is a linear map from the tangent space of M at x to the tangent space of N at fx. So often I will denote this simply by xy alpha, where alpha will be denoting a linear map. So this will be called the 1Z corresponding to certain local maps. Given any such information, you can construct such a map which takes the value y at certain point x with the derivative alpha. It's just a local calculation. So now, suppose this is my notation for RZs of functions, local functions from say some open neighborhood of x into n, because I want to catch only the infinitesimal information at x. So the function just needs to be defined on an open neighborhood of x. So I consider all such local functions, take their rj's. So this is a space of this. So if again r is equal to 1, these are just all possible triples like this. Okay? And then I consider this as the union over Mn. So this is called the rj bundle. Why bundle? Because you have a projection map P onto N. So the fiber over some point x is simply this object. Yeah, r is equal to 0, okay, so I should have mentioned. So r is equal to 0 means this is simply the product space. This is called the J0Mn. So if you look at the sections, they are in 1-1 correspondence with maps. This is the section of the trivial bundle.
In all these examples, we just require for
No. Yeah, for r is equal to, see, whatever regularity you need, you have to take. Yes. Yeah, that is mostly first order differential equation. Yeah, there's a free maps one considers when, okay, so, yeah, there we need, because if you consider the isometric immersion problem, which I stated in the second one, yeah, the second problem, if you want to consider the existence of such equations, then you need to consider free maps. You have to go beyond the immersions and you have to consider the free maps, which is in the second order jets. Also, if you want to talk about Morse functions, then also you need existence, etc. Then also you need the second order things. Okay. So here r is equal to 0 is simply this bundle, and the sections of this bundle are in 1-1 correspondence with the maps from M to N. But for convenience, as far as H-principle theory is concerned, we always view these things as sections of this. But we'll write C infinity Mn. Okay. So this is the structure, but let us only concentrate on J1 Mn, which is over a bundle over N, and an arbitrary element is like this, where alpha is a linear map from Ty N. So just formally think of this as this. Now, when I consider the equation, so that tells you that your rjet has to satisfy certain condition. So I write it this, psi jrfx is either not equal to 0 or equal to 0, whatever. So some relation involving the rjet, right? I'm just plugging in my new notation for that tuple. Now, where does this sit? This is sitting inside the total space of the jet bundle. That means your psi is here a function which is defined on the rjet bundle into some, say, real numbers. If there is just one equation or one inequality, I can view that equation defined by such a function psi. So any partial differential equation means there is some relation. So that relation psi is just a functional relation. So this is a function on the jet space. Okay? So because I have to now look at, suppose I consider this equation, okay? So this one. So this is, I denote this by R. Okay? Then I write F is a solution to the differential equation, let us call this 1, equation 1, I'm just rewriting if and only if its rj at each point belongs to this R. Okay? This is true for all x in R. It's for all x in M. That means what was psi in your case, which was the relation between your derivatives, that is captured by means of some certain subset in the jet bundle. So I mean to say that psi is completely captured by, not psi, the equation 1 is completely captured by the set R inside this. If you want to study the solutions of this equation, let us remove, just stick to 1. This equation, that whole thing is encoded within this subset. Because given that subset, what is the solution? The solution is which satisfies that equation. That means the JRFX belongs to psi inverse 0, that means JRFX lies in R. I'm just restating it in terms of this relation. So this will be the language, in the new language, R will stand for a partial differential relation. Okay? So in the new language, a subset R of the jet bundle will replace the notion of PDE slash PDR. This can be equality, this can be inequality, whatever. So arbitrary subset will stand for a relation. This is the main change in that approach. Okay? Why this is so? Because our question is under what condition on this psi the reverse implication will follow. And then the psi is nothing but that relation R. So we will put some topological condition on R or some geometric condition on R, which will ensure that existence of a formal solution will give rise to a genuine solution. Yes. Yeah, there is no assumption means at least continuity assumption is definitely there. Because in this setup, we will only ask for continuous solution, differentiable solutions. Differentiable solutions means differentiability of order up to R or maybe C infinity, but not below differentiability.
Then you said that an arbitrary of the jet bundle.
Yes. Yeah, solution may not exist in that case. Even the formal solution will not exist. If something is disconnected like this, then this formal equation will also not have any solution. So that question will not even appear. Okay? So here I mean that psi is at least a continuous function. Okay? So basically our maps will have very nice regularity. So this is a continuous function. Okay? So we'll introduce the terminology of H principle now. Okay. So everything I will be writing in terms of functions between two manifolds, but the same thing can be generalized to sections of, this is a smooth fiber bundle and its sections. So the notation would be the space of say CR sections of E. So more generally, we will be considering differential relation for sections of certain fiber bundle. We have already met them because we want to talk about contact forms. What are the contact forms? Contact forms are, first of all, they are sections of the cotangent bundle. Similarly, if you look at the symplectic forms, then symplectic forms are two forms, so they are sections of the second exterior bundle. So the application will be in the level of some smooth fibration as well. But for simplicity, I will just adopt this JRMN so that it is easier for you to think. Okay. So whatever I will write for JRMN, you can write it for, so this space will be denoted by, this is the RJet notation, RJet of sections of E. So these are the notations. So this is alpha, this is omega. Okay. So there will be lots of definitions now. The first of all, we introduce what is a partial differential relation. Oh, sorry. Yeah, all right. A partial differential relation of order R for say smooth maps, okay? Smooth maps can be also CR maps. Smooth maps from M to N is a subset R in the RZ space. Yes. So this is what we mean by a partial differential relation. So as soon as I say something is a partial differential relation, I need to define what is its formal solution, what is its actual solution. So this is the first definition. Second definition, then a smooth map F from M to N is a solution of R if you look at the JRF. What is JRF? Okay, let us define. So JRF will be a section of this bundle. How? It will take X to the RZ of the function f at X. Always remember that RZ of f at X is nothing but the Taylor's polynomial of order R. So this is mapping here, but no, because it's a solution, meaning that we'll have its image inside this R, okay? So now we can compare with that what we wrote. So exactly I am generalizing that statement. So if it's RZ map, this is the RZ map of f is a global function. If its image is lying inside R, then f will be called a solution of R. Similarly, what is a formal solution? A section of the jet bundle. So this is the jet bundle. Section means in the reverse direction. A section of this jet bundle whose image is contained in R is called a formal solution. We shall often refer to it as a section of R. R is not a bundle, so it is not usually said that it is a section of R, but it is here is a section of the Z bundle whose image is contained in R. So these are the three things that we derive from this setup. Now if you look at the RZ map again, so JR, so on one side you have C infinity Mn, and on the other side you have the section of the Z bundle. So I have constructed the JMN as a bundle, and this map is taken F to this. Again, let us look at what is R is equal to 1. So this is J1. Here you have C infinity Mn. I haven't talked about the topology. Gamma on J1 Mn. Okay? So what are the elements in J1 Mn? So I have said that an element in J1 Mn I identify as a triple. So what is alpha? Alpha is a map from Txn to Tyn. So if you look at the section of this bundle, that means for every x I have a map dfx from Txm to Tfxn. In other words, df is a bundle morphism over this. So section, if you have a smooth map, if you look at its associated J1f, that is nothing but the derivative map that we know of. So at each point you look at the derivative of the function f at the point x. So df is a map between the two tangent bundles. Okay? So it is easy to remember here in this case. Now, okay. Now see, we have defined something, solution of R, and here this is a formal solution of R. If you consider this map JR, what is solution of R? Solution of R is nothing but, if you look at the inverse image of the section space of R. This is the notation for sections or formal solutions of R. Okay? Right? See, if you have an F, then JRF is a section of this. If the image is inside R, that is called a solution. So solution space is nothing but the inverse image of the formal solutions under this. In other words, you have this restriction of the RZ map. On one side you have the solution space of R, and on the other side you have the formal solutions of R. So these are the formal solutions of R. And if you look at this map, this is actually an injective map. Okay? So the image can be identified with a subset of this space. Okay? There also you can view the solution space as a subset of the formal solution space. So since JR is an injective map, see, JR is clearly injective. If two functions have some rth order infinitesimal information different, then they have to be different. So since JR is injective, we can view solution space of R as a subset of formal solutions, that means gamma R. Injectivity?
Yeah, because you can take two functions with the same object.
Yes.
And then perturb it in the R plus first level. And they will both go into.
No, this is the function defined, not just at one point. So locally defined, you cannot change, right? Of course, two functions can have the same RZ at one point. But if I say that the whole RZ map is the same, then the function has to be same, because if you look at the second coordinate itself is f. Okay? Yes. This is the globally. At one point, of course, they will be different. Okay. So now, so far I haven't talked anything about topology. Now I will introduce the topology on the function spaces. There is something called compact open topology. I think everybody knows. There is a generalization. Actually, let me tell you. So you know the compact open topology between two topological function space between two topological spaces. So when I am talking about the right hand side, these are certain vector bundles. I look at the sections of the vector bundle. There also I take the compact open topology. Now here, what is the topology? Exactly the topology which is defined by the inverse image of this topology under the RZ map. That means two functions are close provided their rth order information are close. So that is the topology. So the way I have defined the topology, that is called the CR topology, that makes JR continuous. Now I will consider something which is called C infinity topology, which is finer than all the CR topologies, basically the union. Let us not go into this. Just assume that there is a topology which is called the C infinity compact open topology, and on the right hand side just C0 compact open topology, and the way that is defined, JR is automatically continuous. Okay? And not only that, the way it is defined, JR of solution R is a subspace, we can identify as a subspace of gamma R. So here the topology comes into the picture. So solution space, because JR was injective and JR was continuous, I identify the solution space with its image, and that is sitting inside gamma R. The question is how it is sitting inside. So solution R, I just write this. So as a subspace, it is sitting inside the section space of R. Now the question is what? Under what condition on R I should be able to say that given a section here, I would be able to produce a section here. That means this is given a formal solution, I would be able to get a genuine solution. Okay? So of course this is given in terms of homotopy, not just, see, any section that cannot be a solution, but it can be deformed to a solution. So that is what H principle says. I think I can erase this part. So again a definition. R is said to satisfy the H principle if given a section sigma here, there exists a homotopy sigma t in gamma r such that sigma 1 belongs to solution R. Okay. this is a bit ambiguous. I mean, sigma 1 is some rjet of f. See, sigma t, the whole sigma t is lying inside the space of sections. Now, if I say the final map is of this form, then automatically f is a solution. Right? J sigma 1, okay, sigma 1 goes here, and sigma 1 is, this is JRF. So JRF has its image inside R, and then I call F to be a solution. That was my definition. So there exists a homotopy sigma t where the final map is actually coming from a section of, or so for some f in C infinity Mn, so that f is a genuine solution of R. Okay? Now such sections which are sections of R but actually coming from some f are called holonomic sections. Let us not bother, but suppose I say at certain point that I can homotop a section to a genuine solution. I mean this because I have already identified the genuine solutions inside the formal solutions. So there is no harm if I say so. Okay, now let us give some example, then it would be clear.
Do you require every formal solution get homotopy to a genuine one?
Yes, I think the R is said to satisfy the H principle if it will given any section sigma, or given any section.
Some formal solutions may.
Yeah, but H principle will mean that every formal solution can be homotopy to a genuine solution. So again, I have already mentioned these things. Example 1, say I consider f from m to n. Suppose I consider immersions. So that means the derivative of f at x this is injective. So what do I do? In the first jet bundle, I consider a subset R which consists of triples like this, where this is injective linear. So this I will be calling the immersion relation. Yeah. Not only that, I have to assume that it is lying, it has intersection over each of the fibers, right? Otherwise, there is no possibility of getting a global solution. Okay, let's see. So this is your JRMN, and over M, you take the fiber. Yeah, solution R is non-empty, but R is something, is a subset, right? R is subset in the, this is not the function space, this is certain total space of the bundle in which it is sitting inside. See, it may still be possible that there is a subset here, but there is no section which lands inside R. Still that may be possible. See, you have certain bundle and
We started the lecture by saying that we want to show that solutions of R is not empty.
yes. No, not. I said, what is H principle? H principle means that under certain restriction, the formal solution would give rise to genuine solution.
So, a priori, we don't know if there is a genuine solution.
we don't know anything. We don't even know whether a formal solution exists. It only addresses this part of the question. So you can split the question of existence of a solution to the differential equation in two steps. First, the question is whether the formal equation has a solution or not. If that is not there, then there is no possibility of getting a genuine solution. The second step is H principle, means if you have a formal solution, can you get a genuine solution out of that, and under what condition? That is what we will explore.
So when you make this definition, you already seem to assume that there exists a formula.
No.
May I say something? Because I have generally when you have a principle being satisfied by some relation, you have lots of
So this solve R is not true.
Yeah. Generally when it is satisfied. What is, can you?
So in particular existence is given.
Existence
Is guaranteed.
fine. So this definition makes sense only if solve R is not in.
No. Okay, I'll tell you. Means this is just a property. That property may not be satisfied. What it says that given any formal solution, you can deform it to a genuine solution. H principle may not hold for certain solution. We want to study under what condition you can have this property satisfied. Okay.
So this property is even more stronger than existence of difference. Than existence of a solution.
Yes. See, the question is because solving a differential equation is very difficult because you have to guarantee that there is so many regularity. First of all, it has to be R times differentiable. Once you know some other indirect way that okay, it satisfies the H principle, then what we will do, you will just solve the formal thing. If you can show that there is a solution, a formal solution, then there is a solution at this level, means the genuine level. If you can't show that there is a formal solution, then there is no hope of getting a genuine solution. That is anyway true.
I think in spirit, what he's trying to say is that we are not bothered about existence.
Oh no.
H principle is satisfied, then there are lots of solutions.
Yeah, that is the situation I mentioned in the very beginning, that the type of problems that appear in geometry, whenever the solutions exist, they exist in abundance. Okay, so here if you come to this problem, suppose I consider the immersions. Immersions are characterized by this property. So I look at this subset in the J space. Okay. So I look at this subset of the J space. F is a solution of the relation R. So I am recalling the definition. If and only if its associated J1F is a section of this R. And something is a section of this R means what? This is considering all tuple. So what is this? J1Fx is nothing but x, fx, dfx. This belongs to R, and I know that if this belongs to R, that means this is injective. So what is a solution? Solution is something whose dfx is injective. That means F is an immersion. So anything which is a solution of this relation is nothing but an immersion, which I actually expected. That is how I formulated this relation. Okay. Huh.
The argument, how to show that R satisfies H.
That will come. Means I have just developed the language. Sorry. No, nothing. That's the algebraic topological problem.
Yes.
Yeah.
There was some confusion.
Okay. No, that I just mentioned, okay. So there are two steps. You want to show that this differential relation has a solution, means you want to show that there is an immersion. So first of all, what is a formal solution? That means you have to find an injective bundle map this is an injective, this is a monomorphism. So this is the formal solution basically. So this pair is a formal solution. This is a fiber-wise injective map. So given that, if I can show that this relation satisfies the H principle, I haven't shown anything. If I can show that this relation satisfies everything, H principle, then you will just look for such a thing. Once you can guarantee that such a thing exists, you can say that there exists an immersion. So you don't need to solve the partial differential equation. You just solve this topological problem. There is no differentiability involved. This is a fiber-wise linear map, only just continuity. Okay? So that will ensure, so if this R satisfies H principle, then existence of FF as above will imply there exists an immersion F0 from M to N. Okay, so there are two steps. This theorem means what I will be discussing, that is which relations, that means which subsets satisfy H principle, that I will discuss. I will not be discussing whether this has a formal solution or not. That is already taken care of by the obstruction theory in algebraic topology. So given any bundle, whether it has a solution or not, that theory can address up to satisfactorily. Okay? But the differential problem is the most difficult problem, because you need to show that, first of all, produce something which is R times differentiable or whatever times, means depending on the order of the differentiability. Okay. So this statement can equivalently written as this, that this relative group is 0. Oh, not sorry. Okay, what does this mean? I just read. So this map, this is a topological space, this is a topological space. If I can show that this JR induces a bijection between the components of these two spaces, then I can equivalently write that the relative homotopic group, 0th order, is 0. That means what? There are two parts. One stands for surjectivity, which I said that in the H principle. That means given anything, so any component, that will intersect this. On the other hand, suppose you have two solutions, F0 and F1, and you know that they are jets, they are homotopic. Where they are homotopic in the space of formal solutions, then these will be connected by a path of for actual solutions. This is the meaning of this is equal to 0, right? The first part was H principle, which says that given a formal solution, you can homotop it to a genuine solution. The second part says, suppose you have two genuine solutions whose associated formal solutions can be connected by a path in the space of this. Then these can be, F0 can also be connected with F1 by a path. That means what? That means there is a 1-1 correspondence between the components of the solution space and the components of formal solutions. So they are completely classified. This is called, in some sense, a complete classification. There are higher, but I'm not going into that. So if you know the formal solution space, then you will be able to know the actual solution space. But I have just defined the concepts. I haven't told you under what conditions such things happen. So I'll write down the definition now. Shall I keep this or erase? Okay. So. Yes, pi 0 m comma n. So suppose you have some space. This is a subset, and given any point, you would be able to connect it with this. So suppose this is x, this is a, pi 0 x a equal to 0. So given a point here, you would be able to join it by a path, right?
What is pi 0 m comma m?
Pi 0 m. That should be pi 0 m. So here this makes sense because solution R is sitting as A inside this, and X is the gamma R, which is the formal solution space. Given any point in the formal solution space, you would be able to connect it to a genuine solution. So let me write down some sufficient condition where H principle holds. Okay, there are many conditions as we'll see, but we'll later on discuss. First of all, the base manifold N is open. Okay, so that leaves out many nice spaces. Open manifold means what? Open manifold means which is not closed. What are closed manifolds? Closed manifolds is compact without boundary. That means spheres, projective spaces, so they are already ruled out. But if you take out just one point from sphere or projective space, it becomes open manifold. So M is an open manifold. So open means, I'm assuming connected, otherwise you have to change the definition a little bit. Open means not closed, but closed means as a manifold, compact without boundary. So M is an open manifold. Suppose R is a relation in JRMN. So what are the conditions on R? R is open. Second, R is diff M invariant. I will explain. R is open means, see, R is sitting inside this. This has a topology. It is just an open subset of that. See, that means it is again ruling out the equations. Okay? Equations will give you only a closed subset in the Z space. Equality means that. But if you look at the immersions, that is an open relation because it is defined by certain function being non-zero. So they will be coming under this. So 1, 2. Then R satisfies one parametric H principle. Okay. statement is very, very simple. M is an open manifold. Of course, that is a big restriction. We'll see later on how we can also include other kind of manifolds. R is open. Of course, that is a big restriction because all equations are ruled out. R is diff invariant. I'll explain what you mean by diff invariant. Under this condition, R will satisfy one parametric H principle. That means there is a 1-1 correspondence between the components of the solution space and the former solution space. So I first explain this. What is diff M invariant? So I'm looking at functions from M to N. Now diff M, so this is C infinity Mn, and then you have an action of diffeomorphism of M onto C infinity Mn. What is the action? This is simple, just F composed phi. Now when you are considering jet space, how do you define the action? How the jets are defined? For defining jet, you need a local function. That means this is defined on a small neighborhood. This is U into N. So this is a local function. So you need a local diffeomorphism, right? So you need a local diffeomorphisms. So diff M, when I say diff M, is the notation for pseudo group of local diffeomorphism. Of course, they cannot form a group because their domains are different. U to V, V to W, then only they compose. So diffeomorphisms, all other conditions are there, only it's a pseudo group. That means you cannot compose two things, any two things. So you can compose if U to V is there and V to W is there. Only then you can compose. Now if you have a function defined on U, this is some small functions, and you have a local diffeomorphism, then also you can compose this F composed phi. And this action of local diffeomorphisms can be extended to an action on the jets, right? How do you define? Suppose you have a jet, so this is a jet, so F is a local function, say from U into N. U is some open subset of M. So some description is there. And then I take phi, which maps from V into some W which is contained inside U. Okay? So I can compose this phi. Okay? So action is this, phi upper star of JR. This is the most natural thing that we can get. So this is JR F composed phi Y. So Y is going to X. Only thing, everything is happening locally. So there is a local function, I recompose with a local diffeomorphism. Okay? And then take the jet. So this is the action on the jet space. For action on the jet space, I don't need a global action. Only local thing will suffice. So I need an action of this. Okay. So when I say R is diff invariant, so therefore we have an action of, we still call it an action, though diff M is not a group. Diff M on the jet space. Okay? You take any phi, you take a local representative of a jet, recompose them and take the jet. Suppose for every suppose that phi dot JRFX is well defined if the action takes R into R, then we say that R is diff invariant. Okay. Now again compare with consider that problem, immersions. Suppose you have a local immersion, you precompose it with a local diffeomorphism. It remains a remains an immersion. Physically, it preserves the rank. So if you look at the immersion relation, that is open first of all, and also diff invariant. So the theorem says that it satisfies parametric H principle. Okay. So the example, the immersion relation satisfies one parametric H principle. But this was actually a result due to Smell and Harsh. That was not anything new coming out of this theorem. So this is supported by that theorem, but this is a result which was proved by Smell-Harsh. This is known as Smell-Harsh immersion theorem. Actually, this is part of that, but because the theorem is true, okay, let me write the general statement of theorem. It says that if dimension M is strictly less than dimension N, see, if your dimension N is equal to dimension N, then also the relation is non-empty, right? Because you are asking for derivative of f at x to be injective. For example, here it would be isomorphism. That still makes sense. But if dimension of M is bigger than the dimension of N, then the relation is empty. But this theorem says that though the relation is non-empty, if they have the equal dimension, the theorem does not apply to closed manifolds. And you know that. Okay, let me give the counter example. It's a very simple counter example. Everyone knows about it. Suppose S1. You consider any real valued function on S1. S1 is compact, so it will have a maxima as well as minima. So there it cannot be an immersion at those points. So no function on S1 is an immersion. So cannot be an immersion. Okay? But look at the tangent bundle level. What is this? This is simply S1 cross R. You can definitely get a fiber-wise injective map from S1 cross R to R cross R. Let us write one map. So suppose this is the base point B and this is V in the fiber, that going to some point say 0, comma V. This is a fiber-wise injective map. If the theorem were true for closed manifold as well, it would have led to a contradiction. So theorem does not say so. It says only that you have to assume dimension M to be open manifold. So there exists a injective bundle map, though there is no immersion. So observation is that S1 is a closed manifold. that doesn't come under the purview of this theorem. So what Smell has defined is the following. I just express it in a different way. So monomorphisms means fiber-wise injective bundle maps. So take any function f which is immersion, its derivative is a fiber-wise bundle map. This is something much stronger, weak homotopy equivalence, meaning that at each level pi I means the ith homotopy group of this is isomorphic with the ith homotopy group of this. So I just wrote a part of the theorem there. Here there is no assumption on the closeness or openness of the manifold, but you considered this. In that theorem I can talk about the equidimensional case as well in the first theorem. Here I get, of course, this is for all manifold, but then the dimension has to be strictly less than this. And in fact, you can prove this theorem as a consequence of that. You don't need anything extra. Okay, but as I said, these results which came as a corollary to the Gromov's theorem was already known. So what are the new results that came out? Those are the existence of symplectic and contact forms on open manifolds. So these are the corollaries. I'll say something more about this. So it says that symplectic forms, okay, maybe it's not very precise statement, okay, contact forms on open manifolds satisfy H principle, actually parametric H principle. I just write H principle. I'll prove this, and similarly exact symplectic forms on open manifolds satisfy H principle. So this is a somewhat statement is not very precise. Why? So far I was talking about the relation satisfying H principle. Instead I am now saying that contact form satisfying H principle. I mean the relation defining the contact form that satisfies H principle, or relation defining the exact symplectic forms that is satisfying H principle. So I'll prove these results as a consequence of Gromov's theorem. So we'll spend some time on the symplectic case, okay? So let us look at the T star M. So this is my E, this is a bundle over M, okay? And any section, this is a one form, right? Consider the following relation. R so I'm considering an arbitrary local one form and taking its jet, whatever, I'll explain later. So J1 alpha such that d alpha, this is the exterior derivative, d alpha at the point x, if you look at its nth power, suppose n is 2n, this is not equal to 0. That means d alpha is a symplectic or non-degenerate at the point x, okay? But what is the relation between this and this? This is the derivative in the usual sense, and this is the exterior derivative. They don't match for forms. Okay? Okay, let us work locally. So locally, any alpha that looks like alpha is equal to summation alpha I dxi, I is equal to 1 to 2n. So x1, x2, x2n is the coordinate system. Simply think about that we are working in R2n. Just one form in R2n will look like this. So these alpha i's are functions of the base space, right? Alpha is a form. So alpha x can be written as summation alpha ix dxi. So what is the jet information? Jet means basically you consider the derivative of these functions. So this information corresponds to del alpha I del xj, where ij is from 1 to 2n. So this is the information for the one jet. One jet means what? The derivative of all the component functions. Alpha has the components alpha 1, alpha 2, alpha 2n. So its derivative means all possible first partial derivatives of the component functions. On the other hand, what is d alpha? D alpha at x is summation d alpha I x dxi. I is equal to 1 to 2n, and then this is del alpha I del xj wedge. This is dxj wedge dxi. I is equal to 1 to 2n, and then you can write it as del alpha I del xj minus del alpha j del xi dxj wedge dxi, here I less than, or sorry, j less than I. This is the expression. So what is happening? If I am starting from j1 alpha, my condition is given as d alpha. But if I have to apply each principle, I have to realize the condition on the jet space. Where does this sit? Let us see first. D alpha x is a section of this, right? Of this. It is not the jet bundle. You have to consider the one jets of all these things. Qm as locally R2n. So your relation means that J1 alpha is captured by these. Sorry, I missed out some more information. Also the alpha i's. The values are also part of the jet, functional values, and they are first partial derivatives. Whereas when you look at the d alpha part, then these are only a relation in terms of this. So let's see what is happening. So you have the jet bundle J1. Okay, my notation would be, this was T star M, that was my M, E. So this is the one jet bundle notation. And from there, you are going to two forms, right? Sections of this is a two form. Okay, I write in the bundle level. So this is lambda 2 T star M. Now here the jet is sitting inside here, and here you have d alpha x. And this is the map which is taking J1 alpha to d alpha. What is the map? Map is given there. So information is alpha I del xj. This information is going to the information this tuple I less than j or some. Okay. So there is no reflection of these functional values, so keep them fixed. So what is the fiber of this? Now if you look at this thing at the point x, you get a matrix, right? N by n matrix or 2n by 2n matrix. Coefficients are del alpha I, del xj, x. You get a matrix. And what is this? I think this is right? This is A minus A transpose. So you can show that the fibers are contractible. So this is first of all onto map, and look at the fiber of this map, A going to A minus A transpose, so the symmetric one. That fiber, you can make it contractible. So it says that you can have a section in this direction. Let us call this, phi. Okay? Now come to this. I define R to be actually delta inverse of non-degenerate linear two forms. This is a non-degenerate form which is sitting inside lambda 2t star m. So, and this is the inverse image of that. This is an affine subspace because I have ignored the alpha 1, alpha 2, alpha n. So now this will be becoming the affine subspace here. As I said, this is a surjective map whose fiber is contractible. Non-degenerate two forms, they form an open subset. So R will be open. This will be invariant. So I can say that this R is open invariant. Okay, invariantness is clear. If you have a non-degenerate form, if you pull it back, what is the natural action here? Earlier I was considering C infinity Mn. So the natural action of the diffeomorphism group was recomposition. In a sense, pull back. Here also you have forms. So the natural action of the diff is also the pullback. So if something is a non-degenerate form, if you pull it back by some diffeomorphism, it is still non-degenerate. So, right hand side, if you look at this set, non-degeneracy is an open condition. Something is non-degenerate, something close nearby will also be non-degenerate. So this is a non-degenerate diff invariant subspace. When you come here, that is still non-degenerate and diff invariant. So R is open and invariant. So for this, there will be this theorem will apply. Okay? So what is the statement there then? It says that this J1 from all one forms on N such that d alpha is symplectic from here to gamma of delta inverse R. This is a one, okay, this defines a bijection between the components. Okay, that is what H principle says. But see, it is difficult to say something in terms of the Z spaces. Rather, we will talk in terms of the sections of this bundle. Let's see. So our relation, so this was R, our final relation is delta inverse R. So what does H principle says? It says that if this has a section, then there will be a exact symplectic form, right? Because delta inverse R satisfies H principle. That is a subset inside your first Z bundle. This satisfies H principle. So if this has a section, then you have a exact symplectic form. But how do you guarantee that this object, which looks very complicated, this has a section? Instead, you simply look at this bundle and show that this has a section. Because given a section here, composing by this capital phi, you can go here. So you get a section here. As I said that this is onto map and the fibers as contractible, so you have a map going into this direction, which is a section. So you start from, so let us look at this. Suppose you have a omega. You go to capital phi of omega. This is a section, so phi omega is a section of delta inverse R, and which satisfies H principle. And what are its solutions? Solutions are all exact symplectic forms. So start from a non-degenerate 2 form on the manifold, I have defined a exact symplectic form. See, non-degenerate 2 form, this is purely topological. There is no differentiability. So if you can show that there exists a non-degenerate 2 form everywhere, then you can conclude that there is a exact symplectic form, which is a differential problem. Okay, so we'll continue in the next class. So this proves that on open manifold, the exact symplectic forms satisfy the H principle.
Are there any questions?